In this video, I want to explain as concisely as possible and with very simple examples what Redshift is. Additionally, I want to mention the incredible discoveries we have been able to make based on this quite simple phenomenon. The easiest way to explain Redshift is probably through the Doppler effect. The Doppler effect is observed with sound waves, whereas Redshift occurs with electromagnetic waves, such as light, among others. The Doppler effect can be easily explained with a stationary or moving ambulance, because we have all experienced this. If the ambulance is stationary with its siren on, the sound waves spread out evenly in all directions. The wavelength of the sound waves is the same in all directions. This means that if I hear this stationary ambulance from the right, it sounds the same as if I hear it from the left. It is different, as already indicated, with a moving ambulance. If it has the siren on, the sound waves compress in the direction of travel. This means we have different wavelengths depending on where I am listening from. If I listen from the left, the waves are longer, and the sound is different than if I listen from the right, because we have different wavelengths. At this point, I would like to play how it sounds when you stand in one place and the ambulance first approaches you and then moves away. We have probably all experienced this. What is the deal with the redshift now? To explain this, let's consider the following model. On the left in the image, we see our Earth and hovering above it, so to speak, a telescope, our Hubble telescope. This Hubble telescope is currently observing a galaxy or a star visible on the right in the image and is receiving electromagnetic radiation from it, which means the light. The whole thing is not to scale. The important thing is that the two are very far apart from each other. The star or the galaxy is very far away. I have already indicated the direction of movement of the star or this galaxy with the arrow. This means that this star is moving away from the Hubble telescope. Now we can remember the ambulance and reconsider what that would mean for sound waves. They would be compressed in the direction of movement. Now this star does not emit sound waves, and the Hubble telescope is also not built to measure sound waves, but rather electromagnetic waves, as already indicated. That means light, infrared radiation, and so on. Fortunately for us, waves generally behave quite similarly. To better understand this, let's take a look at the electromagnetic color spectrum for assistance. On this spectrum, you can see every conceivable wavelength of visible light, and which color results from it. This means that the color is always dependent on the wavelength. As we can see, the star has a yellow color. This means we could locate it approximately here on the spectrum. If you now recall the Doppler effect, the wavelengths in front of the star in the direction of movement appear to be compressed. This means the wavelengths become shorter and are shifted, for example, towards blue. This is the so-called blue shift. Here we are already hinting at what the red shift might be, but let's quickly go through the blue shift again. The wavelengths in front of the star in the direction of movement are compressed, so that they would be shifted towards blue. The yellow light then appears more bluish. This means that the light observed from the front would appear bluish. Behind the star, as already indicated, the waves are stretched. This means that the originally yellowish light is shifted towards red, the so-called redshift. So what the Hubble telescope observes from this star is not the original yellowish color, but red hue. And that is the redshift. With this redshift, we can determine in which direction a particular celestial body is moving, depending on the Hubble telescope. Is it moving away from it or coming closer? Now, the Hubble telescope does not only observe one star or galaxy, but looks deep into the interstellar space. And what was discovered there through the Hubble telescope was that the galaxies are all moving away from each other. Although the gravitational force should naturally ensure that everything moves towards each other. Additionally, it was also observed that the farther the galaxies were, the faster they moved away from each other. This means the conclusion was drawn that the universe is expanding. From this observation, a theologian and astrophysicist drew the clever conclusion that if everything is expanding now than in the past, everything must have been closer together. That means, if it is expanding now, and I turn back time, then everything would contract. And there is a point in time when everything was united in a single point, a so-called singularity. The founder of this theory was Lemaitre. And this theory is nowadays known as the Big Bang theory.